Hello, we are now in RFOptic. Today is Monday, the 3rd of March 2020, and we are going to show you a demonstration requested by ISRO SAC in India. The demonstration will show you how we measure a delay of fibers in an optical delay line system. So we'll start with the optical delay line. What you see here is the TX unit and the RX unit of an optical delay line. And you see a fiber which is connecting the two units one to each other. This together represent an optical delay line in general. One have a bigger enclosure, 19-inch 3U typically, where these two units are integrated into the enclosure, together with an array of switches, different delay lines, etc. But currently this represents, and this is a 40 GHz RF over fiber, okay, based on the request of SAC to demonstrate the measurement with a 40 GHz system. Okay, the way that we are going to measure the delay, we are going to measure the delay of this fiber, okay? This is a fiber of about 15.2 meters. But before we do that, we have to set the zero delay line of the optical delay line. The zero delay line is defined by the internal delay line of the optical delay line system without the fibers, okay, without. Why? Because in the system inside, before using the delay line fibers, there is some short fibers of 1-2 meters of the optical switches and other, which are connecting the whole system. And eventually the system, even without any delay line, have some internal delay, which is denoted again by the zero delay line, which is typically between 10 to 50 nanoseconds. This zero delay line is measured one, it's fixed, it does not change. And then to this zero delay line, which the customer knows, one has to add the different delay line, which can be tens of nanoseconds up to hundreds of microseconds, okay? The way that we are going to measure the zero delay line is as follows. We are using a pulse generator of Avatec. It creates pulses of about 2.8 nanoseconds, we can say roughly 3 nanoseconds, which are coming through this coax, okay? And we control the pulse shape here. Here we can control the offset of the trigger. In a minute we'll show you how, okay? So this system, this pulsar is connected with this coax to the TX unit here. The TX unit is connected with the short fiber currently to the RX unit here. And then the output of the RX unit is connected to the scope here. Currently the scope is in freeze mode. The trigger is connected to channel 1 here, and you see on the other side is connected, of course, to the pulse generator. Now we will take the system from the freeze mode in a minute. Before that, I would like to explain you an important point. You see here the pulse, it's in the yellow, okay? This pulse, if we measure it, hold for a minute. So we will use the cursor here. I put it here on the yellow in the middle, about, and I take the second one, also put it on the other side of the, okay, and you see it's about here 3.2 nanoseconds. Of course this is about the pulse width, which is denoted by the yellow line. The red line is the trigger. So what we do, I'll take the cursor out. The yellow line is exactly on the middle of the scope, on this line, and you see also the middle of the slope of the red line is also at the same place. So between them there is 0 offset. Now what we will do, we'll take it out of freeze mode, and Guy, okay, it's out of freeze mode, and Guy will play with the offset. Play more, take it more to the left, more, right, no, right, okay, right, left, you see, he's playing with the offset. Now Guy, slowly move back, slowly, okay, stop, a bit more, slightly, okay, stop. We will freeze it again, and you see, just a minute, okay, and you see that again these two pulses coincide here, and you see that the trigger is more to the right, okay, sorry, just playing with the cursor, okay. Now what we will do is, in a minute we will add this fiber, okay, this 15 meter fiber, and what will be is that the red pulse as compared to the trigger, the red line which is the trigger as compared to the pulse which is here, will be offset such that the red will be go to left and the yellow right, and there will be create an offset in between them. Okay, so we will take it out of freeze mode, okay, and Guy, please connect the 15.2 meter fiber to the delay line. Okay, so you see the signal came back. We will freeze it again, and you see that now the red is shifted left. Of course, this is in comparison, okay, the yellow shift right or the red shift left, and let's measure now the distance that the red shift left. Before, this red line was here in the middle. Now it shifted to the left. Let's see how much. So we'll take the two cursor, we'll take the two cursor. So the first one we'll put here, in the middle of the, okay, you see here in the middle of the white line as before. And we'll take the second one, and we'll take it to the middle of the slope here, okay. And you see now, basically, we exactly measure the shift in between, and the number here, as you see, is 75.6 nanosecond, which is basically the delay created by this 15.2 meter fiber that we added here. So we measured successfully a 75 nanosecond delay line very easily. And you can easily understand that even if you will take a shorter fiber of 30 nanosecond, we can measure it easily. For sure, it's much easier to measure microsecond fiber and longer using the scope. Thank you very much. Bye-bye.